Today we will talk about the Morison equation example. The Morison equation is used to calculate the hydrodynamic forces acting on the cylindrical structure submerged in water, especially under wave action. This section provides a detailed explanation of the equation, its components, assumptions, and limitations also, and includes a numerical example for clarity. You can see Morison equation is the summation of drag force as well as inertia force. Here you see F is the total hydrodynamic force vector per unit length acting normal to the member's axis, Newton per meter or foot pounds per feet. So here we can see the components of the force. Drag force. Drag force is the Fd equal to 1 by 2 into drag coefficient W, like W into A into U and U. Here you can see CD is the drag coefficient, that's dimensionless. W is the weight density of the water. A is the projected area normal to the cylinder axis, and U is the absolute value of the velocity component normal to the member axis, and another U is also same water velocity component, water velocity vector component normal to the member axis. And inertia force also you can see Fi is Cm W V dou U by dou T, like Cm is the inertia coefficient, that is dimensionless, typically around 1 for circular cylinders. V is the displaced volume of the cylinder, and dou U by dou T is the local acceleration of water normal to the member axis. Assumptions and limitations. If you see inertia force calculation, Morison equation simplifies the inertia force by excluding the convective acceleration component. So it is excluding the convective acceleration component that we will see in detail. And neglected forces, if you see, equation does not account for lift force, lamp force, and axial fluid correlative forces. So three forces it's not including, does not account for that. These are the neglected forces, and this equation is applicable most accurate when the diameter of the wave diameter is small related to the wavelength. So this is the diameter, for example, D, and wavelength, this will be the wavelength. So if this diameter is small related to the wavelength, if not diffraction theory should be asleep. If this is a diameter say 1 meter, then wavelength should be greater than 5 meter. If it is the case, then this Morison equation applicable. If not, the diffraction theory should be used. Let's see this numerical example. Calculate the total hydrodynamic force on the circular cylindrical member submerged in water due to the wave action. Diameter is 0.5 meter, drag coefficient 1.2, weight density is 10,000 Newton per meter cube. Velocity of water normal to the member is 2 meter per second. Local acceleration 1.5 meter per second square. Inertia is 1.00, area is 0.5 meter, volume is 0.193, and drag coefficient drag force we can calculate by 1 by 2 into CD into O into A into U into U. Substituting those values, we can get drag force 24,000 Newton per meter, and the same way inertia force we can calculate Cm into omega into V by dou E by dou T. If you substituting the values, we will get 2944.5. This is 24,000, this is 2,900. So if we add these two, then we can get 26,944. So the total hydrodynamic force acting on the cylindrical member is approximately 26,944. This example shows that how to apply Morison equation to determine the forces exerted on the submerged cylindrical structures under wave action, taking into account both drag and inertia forces. Understanding these calculations is crucial for ensuring structural integrity and safety for marine installations. So we can see what is the Morison equation used for. What is the Morison equation used for? The Morison equation is used for calculating. They used to calculate the hydrodynamic forces acting on the cylindrical structures submerged in water, particularly under wave action. What are the two main components of Morison equation? That is, two main components are drag force and non-Morison inertia force. What's the significance of drag coefficient in Morison equation? The drag coefficient is a dimensionless number that characterizes the resistance to the cylindrical member to the fluid flow. It varies with Reynolds number as well as affects calculation of the drag force. How is the projected area of cylinder defined in Morison equation? Projected area defines the effective diameter of the cylinder member measured in square meters or square feet. What is the condition under which Morison equation is most accurate? What's the condition under which Morison equation is most accurate? The Morison equation is most accurate when the diameter of the cylindrical member is relative small relative to the wavelength of the incident waves, specifically when the ratio is lambda by d is greater than 5. That means lambda should be greater than 5 times diameter. What does the inertia coefficient Cm represent the inertia force calculation? Inertia coefficient represents the contribution of water's inertia to the force experienced by the cylindrical member. It is typically around 1.04 as numbers. What are some limitations of Morison? The limitations of the include exclusion of convective acceleration, lift forces, slam forces, axial forces, which may be significant in certain conditions that it's excluded from this. These are some limitations. When should diffraction theory should be used instead of Morison equation? Diffraction theory should be used when the member width exceeds 1/5 of the incident wavelength. As in, this indicates the significant wave scattering or diffraction effects. In the provided numerical example, what was the total hydrodynamic force calculated? Total hydrodynamic force is 26,000. How does the weight density affect the forces calculated? Weight density directly influences both the drag and inertia coefficients. Higher the water density increases the forces, resulting in the greater the hydrodynamic forces in the structure.